is Andrea Marcano, and I currently work in Nokia Bell Labs in a standardization research group. And I will be presenting to you today a seminar about bandwidth parts. And this is a topic that I've been working with for almost 2 years now, and it's one of the key features for 5G networks. And the results and everything I will present here, they have been done in collaboration with my colleague Fuad. So after the seminar, if you have any doubts, then you can reach me or you can reach Fuad as well. Alright, so the title is Bandwidth Bar, a 5G feature for improving spectrum flexibility and power savings. So first I will present you the agenda for today. So I have a part of introduction, which I will explain why we need bandwidth bars, why this concept was introduced in 5G, and what they are actually. Then the basics of bandwidth bars, so we will go through the configuration of bandwidth bars, and I will present two examples of resource allocation, one for LTE and one for NR, where we use bandwidth bars, so you can have a clearer idea of what we use them for. Then third point will be bandwidth bar adaptation, then some use cases for bandwidth bars, and then I will present some results of the work we have been doing. So these are the studies on impact of bandwidth bar switching on 5G system performance. So here we will go through some of the issues that come with the implementation of bandwidth bars, the methodology that we use for doing the simulations, and then some results. And then I will wrap up with the conclusions, highlighting the most important findings that we have so far, as well as some future directions that we would like to explore. And if you have any questions, feel free to just ask them either at the end if you prefer, or just raise your hand. All right, so let's start with why bandwidth bars, why this concept was introduced in 5G. So first we have NR. NR is a new radio, is the new standard for 5th generation mobile networks. And in this standard, very wide carrier bandwidth are introduced. And when I say very wide, I mean that up to 100 megahertz for FR1, and those are the set of frequencies below 6 gigahertz, and then up to 400 megahertz for frequencies above 6 gigahertz. This is much wider than what we had in LTE. So this is a new key characteristic of new radio. And then the question is, how can we support this wide bandwidth? And we mean, how can we support it from the user equipment perspective? Because then it's wide, so it requires a lot of processing from the user equipment. So we can allow this by having a receiver side bandwidth adaptation, which means that from the receiver side, maybe we can do something that doesn't require monitoring the whole carrier bandwidth. And if we manage to do that, then we can reduce the complexity from the user equipment to not have to monitor this either 100 or 400 megahertz. And then these 100 and 400 are without carrier application, so eventually it could be much wider. Then another key feature is that in 5G we have 5 transmission numerologies. Then what is a numerology? It's a combination of subcarrier spacing and a cyclic prefix. So if we remember a little bit in the theory of OFDM, then the subcarrier spacing is just the space between the maximum of the subcarriers, and it influences the symbol time. So in LTE we only had one subcarrier spacing, and that was 15 kilohertz. But now in 5G, 5 transmission numerologies were introduced, and they were introduced in order to support different kinds of services. Again, for LTE, it was designed mainly for mobile broadband. But then for 5G, we consider other things. We have enhanced mobile broadband, so it's much faster. But then we also have machine-type communications and URLC, for example, which are it's a kind of service that requires very low latency. So in order to adjust the system to all of these different services, these numerologies were introduced. And as I said, they influence the symbol time, and hence they allow to support services that require lower latency. And then how to support the different numerologies is the question. Then we cannot continue with the same scheme that we had in LTE, again, because we only had one numerology. So in order to do that, we have the GNOB, and the GNOB is the base station. That's the name that it receives in 5G. And the GNOB assigns the resources to each UE according to its service needs. So it's selective now. The network, depending on the service of each user, it will allocate certain conditions in the bandwidth. Okay, so now it's not the same kind of allocation for everyone. Now it's a selective allocation. And then, again, we have these two things. Then we say, okay, we have a bandwidth adaptation, and now we also have a bandwidth adaptation that depends on each kind of service. So what can we do in the carrier structure, in how we allocate the services to support this? Then to this, the concept of bandwidth bars was introduced. So basically, it's a feature that allows for this bandwidth adaptation, and at the same time, it allows supporting different kind of services with different requirements at the same time in the same carrier. So let's go more with its concept per se. So we have bandwidth bars. They are user-specific bandwidth partitions in a given carrier. So again, because it depends on the user service, it's a concept that is user-specific, meaning that two users, they not necessarily will have the same configuration of bandwidth bars. They could, but they're not obliged to. Okay, so each user in the network could have a different bandwidth bar configuration. Then it's a group of contiguous resources, well, in this case they are called physical resource blocks, that share a common numerology. So meaning that the network will assign a chunk of bandwidth to a user with certain characteristics depending on that user's service. And one of those characteristics is that all that chunk of frequency has to have the same numerology. Okay, so it's either, as I mentioned before, we have 5 numerologies, and depending on the frequency range they use, some of them are allowed and some others are not by the standard. Then the network knows that and will say, okay, if you have enhanced mobile broadband service, then I will assign you a chunk of frequency with this numerology, and that will be your bandwidth bar. And then for another user that probably has URLC, then it would be another chunk of frequency with another characteristic. And that's how we define a bandwidth bar. Then this concept of physical resource blocks, if you are familiarized with it in LTE, then all the resources in LTE receive that name. In new radio it's a bit different, and in the 1 or 2 slides ahead I will go a little bit more in detail with that. I will go through the seminar in too much details in how these resources are named, but if anyone then wants some more information, you can ask me. Then, okay, so now what do we achieve by having bandwidth bars? We can allow the spectrum flexibility, which means that we can multiplex narrowband and wideband users. Why narrowband and wideband? Because depending on the user capabilities, then that bandwidth bar can be very small or it can be very big. And when I mean very big, it could be all the carrier bandwidth if you have a user equipment that has the capabilities to decode and monitor the whole carrier bandwidth, or it could be a very small chunk of that carrier. Okay, and it can also multiplex the different numerologies at the same time. And this is the most critical aspect, perhaps, of bandwidth bar, because it's the best way that in an hour you can simultaneously in the same carrier support different kind of services. And then if we go deeper into one of the key aspects of 5G is precisely that, is to offer the support of a variety of services. It's no longer a system that focuses only in mobile broadband. So this is a key aspect of bandwidth bars. And then we also have that it allows for power savings because the UEs are not forced to monitor the whole carrier bandwidth. So again, this is if the UE has to monitor the whole carrier bandwidth, it will of course require more power from the UE. So if we have a user equipment that has the capabilities of doing so, then that's great. You might simplify things and just assign a bandwidth bar that's the whole carrier. But if you don't, then you can assign a smaller chunk, and then that user will use less power. And in this way, you can save power eventually. And so this is another one of the key things that you can achieve by using bandwidth bars. So now let's see here, how do we configure them? So now we know what they are. They are user-specific chunks of frequency, and they share the same numerology. But how do they get configured in each UE? So we can have up to 4 in the uplink and up to 4 in the downlink for each UE in a given serving cell. So at this point, we're not talking about carrier aggregation or anything. It's just in one carrier, a user can have configured up to 4 different bandwidth pairs in the uplink and 4 different in the downlink. And again, if we say a different bandwidth pair is simply one can be smaller, one can be bigger, one can have numerology 1, the other one can have numerology 3, and so on. But only one of those for downlink and one of those for uplink can be activated at a given time. Meaning that the user, although it has a stored configuration of 4 of them, it can only transmit and receive signals in one of those bandwidth pairs at a given time. Okay? And this is to avoid, of course, the conflict of a user having to monitor at the same time, for example, 2 different numerologies, or if you have bandwidth pairs that in the configuration they overlap in frequency, then of course that would create a conflict for the user to have to monitor that at the same time. So it stores a configuration, and the reason of storing this configuration is that if the network sees the need to change the configuration that the user is using at that moment to decode the signals and to transmit, it can do it very fast. It can go and say, okay, you have stored these 4 configurations, use configuration number 1 or 2 or 3 or 4. So it's just to have them to access them very easily, but only one of them will be active at a given time. And then, as I said before, the configured bandwidth pairs, they can overlap in frequency. Again, this won't create a conflict because only one of them will be active, so you can configure however you want in the spectrum or the network in this case. And they are UE specific again, so each user can have a completely different configuration of the 4 bandwidth pairs. So if we see this example here in the figure, this could be for one user, for example, and it can be bandwidth pair 1, it's almost a little bit more than half of the carrier bandwidth. Then we have another bandwidth pair 2 that it overlaps in frequency, but is not active at this time, so it doesn't create any conflict. Then we can have a third one that is the whole carrier bandwidth, and then we can have a fourth one that is very small. So this really depends on the network conditions, on the load, on the user capabilities, and this is something that the scheduler from the network side will decide how to configure. Okay, it's up to implementation, it's nothing standardized. And then, for example, if we see a whole carrier bandwidth operating, we could see that all of this can be active bandwidth parts here. And this is for user 1, this is bandwidth pair 1 for user 1, and this is bandwidth pair 1 for user 2. So you can see that they are not the same. They are, again, user specific, and this is very important to keep in mind because it's one of the things that add complexity to using bandwidth pairs. And then we can have, for example, bandwidth pair number 4 for UE3, and so on. Yes?
So something which is decided by the manufacturer of the UE or the network? I mean, what handset does...
No, the configuration is decided by the network.
By the network?
Yes.
For each UE?
For each UE, yes. So each UE, depending on the type of UE, it has different capabilities about the configuration of bandwidth pairs. But so far, all of them can have up to 4 bandwidth pairs configured. But then it's up to the network to configure them. It's not, it doesn't depend on the user equipment manufacturers. So it's all up to the scheduler to decide how to do that. All right, then let's see some other characteristics of the bandwidth pairs. Then in size, they can vary from 24 to 275 PRB. So you can see there's a big difference here in terms of how many resources the size of a bandwidth pair can be. And this is exactly where the multiplexing of narrow and wideband users and the power saving benefits come from. Then some restrictions is that the size of a bandwidth pairs, of course, cannot be larger than the maximum bandwidth supported by a UE. So something that would be, for example, depending on the manufacturer of the UE, would be what's the maximum bandwidth that it can support. But then it's up to the network to decide, based on that, how to configure the bandwidth pairs. And there's no reception or transmission of signals outside the bandwidth pair. This is, again, where power saving comes from. So the scheduler must limit the resources allocation for control and data within the bandwidth pair. So again, in an example that I will show ahead, we will see that for LTE, users are obliged to monitor constantly the whole carrier. If we do that in NR, it comes with a lot of power consumption. So some users might be able to do that, some users no. So the scheduler is the one that must limit the resources assigned inside the bandwidth bar. Because by definition, and this is by the standard, the user should not monitor anything outside its active bandwidth bar. And then we have three types of bandwidth bar. We have an initial one. This is just the names that these partitions receive depending on what they are used for. And there's an initial one, which is used for the initial access to the network and for the broadcasting signals. And then this one is like a particular bandwidth bar because it's common to all UEs, and it's the only bandwidth bar that has that characteristic. So although bandwidth bars are UE specific, all of them share the initial bandwidth bar. And this initial bandwidth bar is set by the network and is informed to all the UEs when they connect to the network. Then we have a default bandwidth bar, which is where the user goes to, or the network tells the user to go to that default bandwidth bar when it's going through inactivity periods. So if the UE is going through some inactivity periods, then for the network it goes like, okay, you could save some power right now because you don't have a lot of data coming and going, so there's no need for you to monitor the whole carrier bandwidth, for example. So it moves the user, like move it means that it sends a signal saying switch to the default bandwidth bar. And normally the default bandwidth bar should be a small one because it allows for power saving. And then there's a dedicated bandwidth bar. It's just simply the kind of bandwidth bars that are assigned individually to each UE. And normally they are wider than the default bandwidth bar, and this is where data transmission should happen. And then we have another one that is called first active bandwidth bar, and this is only valid in the context of carrier aggregation, and it's just a bandwidth bar to which a user connects when, sorry, not carrier aggregation, dual connectivity. It's the bandwidth bar where a user connects when it connects to a secondary cell in the context of dual connectivity. All right, so let's move now to the example so you can have a better idea of what happens in the scheduler when you have to deal with bandwidth bars. So we see here an example. Oh, I think you cannot see here too well the colors. Here. Well, this is orange. Okay, great. All right, so in this example, we have a network with one INO B, because this is an LTE example, and we have two UEs. And this is an illustration of the carrier bandwidth. So we have here in frequency, and we have a carrier that starts in F1 and it finishes in F2. And as we can see, it's divided in PRBs, which are the physical resource blocks. So normally how it goes is, all the elements in the network, they see the same carrier. So all of them, they see a carrier that starts in F1 and finishes in F2. And they see a carrier that is divided, in this example, in 10 PRBs. And then the network, well, all of them have to handle and monitor the whole carrier bandwidth, okay? And from the network side, it assigns the resources to the UEs based on PRBs. So it sends a signal with some information and it says, okay, for you, user 1, in this case, you will have PRBs from 1 to 3. So that's the chunk of frequency where you can transmit and receive signal. So anything that goes there is for you. And then for user 2, it just assigns a different chunk of the frequency. In this case, it will be from PRB6 to PRB9. So again, as you can see, they don't overlap. They shouldn't overlap, never. But from the network perspective, it's very simple. I know that both users are seeing the same thing that I'm seeing, and I just have to tell them from which PRB to which one they are going to receive signal, or they are going to send signals in case of the opening. And this is how it happens, the resource allocation in LTE. Of course, then it has more complexity into how to optimize which users transmit at each time. But from a frequency point of view, this is pretty much how it happens. But then we have, okay, but now let's see in the case of NR. And then you see here a figure that is way more complicated. And just by this figure that is way more complicated, you should have an idea that the scheduler for NR is going to be way more complex and has things to solve that are way more complex than for LTE. Okay? So here, what happens? We have the same network, but now each one of the elements, they can have a different vision of the carrier. Okay? except for the GNOB. In the case of LTE it's called GNOB, for NR it's called GNOB. The GNOB, it keeps seeing the whole carrier. So in this case, it would see from F1 to F2. And of course, because it's like the mastermind, it can see all the users and it will allocate all the users accordingly to avoid any conflict or whatsoever. But that's not the same thing that the users are going to see. So each user is going to see a different version of the carrier, depending on its service and depending on its bandwidth bar. Okay? So if we look at user 1, for example, which is this blue one, it will get this portion of the carrier bandwidth assigned. But actually, for this user, the carrier starts here, where I think you can see here where first usable PRB is, and it finishes. Sorry, here in CRB3, it starts here, and it finishes here. Okay, so this is the how can we say? This is the grid of resources that the user sees. Okay. Why that grid of resources? Because that grid of resources follows certain numerology, and is the numerology that at that moment that user can have access to, is configured to use. So for this user here, UE1, it sees this, but this is transparent. Okay, whatever configuration other users have, it's transparent to each one of the users. They don't need to know that. And then for user 1, it will only monitor this chunk of frequency here. Okay? And as you can see, it's labeled from PRB0 to PRBN, because the labeling happens, it starts from 0 in each bandwidth bar. So then again, you see that it's a completely different vision for each user. So what might be a PRB0 for one user is not necessarily the same PRB0 for another user. And this is where it gets very complicated for the scheduler, because then it has to, in a very smart way, allocate the users in an optimal way to avoid losing any spectrum, but at the same time trying to multiplex narrowband and wideband users at the same time as different kinds of services. And then in a similar way, we see user 2 here, then what it sees as a carrier is this one here, okay? And it will only monitor from PRB0 again to PRBM, but this is in a different set of frequencies, a different chunk of frequency, and it's using a different numerology. If you can see here, the space in between the PRBs is wider here than here, for UE2 than for UE1, because they're using different numerologies. And so it's very complicated if we want to thoroughly analyze how the resources scheduling happen in NR. And all this complication comes because of the use of bandwidth bars. And then there's a problem that has to be considered, and it's the fact that when you have one numerology next to the other, you have to have a guard band in between the two numerologies, because otherwise you get what is called internumerology interference. So again, from the scheduler, it has to, in a very smart way, select which users to allocate at a given time, and how to allocate them in the most optimal way to avoid losing a lot of spectrum due to guard bands and so on. And yeah, so again, this I won't go into every detail of how to configure this. If anyone is interested in this, it's very hard to get it from the standard, but you can reach to either Fuad or myself, and we can give you more details about it. Okay, so let's move to the bandwidth bar adaptation. Now we know what they are, how they are configured, what kinds of bandwidth bars we have. And now let's see, this bandwidth bar adaptation is how we switch now from one to the other. We know we can have up to 4 configured, but what do we do with that? How do we switch from one to the other, and how does that impact in the network performance, if it impacts in any way? So we have a bandwidth bar switching, which is a procedure through which an active bandwidth bar gets deactivated and a deactive bandwidth bar gets activated. So it's simply switching from one bandwidth bar to the other. And because only one can be active at one time, we have to deactivate the one where the user is working at that moment, and we have to activate another one. Okay, and this process is what is called the bandwidth bar switching. Now, this bandwidth bar switching can be triggered by different ways. So one can be the control signal from the network. It's called downlink control information. and it allows activating in a very fast way any of the configured bandwidth bars. So before I mentioned to you, we can have up to 4. And the reason for having this is that the network can very quickly go and say, okay, switch from bandwidth bar 1 to 2, or from 2 to 3, or so on. And this quick switching is done through DCI. So this is the best way perhaps to switch if we want to, because it avoids latency. Then there's another kind of switching that comes from upper layer, so it comes from radio resource control. And if we do this kind of switching, it actually allows to introduce or to change the configuration that the user already has. So if the user has 4 bandwidth bar configures, the network knows this, but certainly goes like, I would actually like you to have one configured differently than what you have right now. It can do that through RRC. So it will send a bandwidth bar switching command, but along with that command you will have all the configuration of that new bandwidth bar. But this of course comes with more latency. So this is the one that should be used only if strictly necessary. Then we have another one that happens through the MAC entity, and this is when the user performs random access. Then it's the MAC entity the one that configures a bandwidth bar, and it would be same as RRC, a new bandwidth bar. So this also is slower than switching via DCI. And then we have another one, which is the bandwidth bar inactivity timer, and this one is also the one that eventually, in the results that I will show ahead, is the one that we have evaluated the most. So we have an inactivity timer, which means that this timer switches the switching of a dedicated bandwidth bar, so a wide bandwidth bar where data is happening. But then what happens if suddenly there's data inactivity? And then the network goes like, okay, there's no need for you to stay there monitoring nothing but consuming a lot of power. So we have this bandwidth bar inactivity timer. If that timer expires, then by default, just automatically the user will switch to the default bandwidth bar. And now if we remember the type of bandwidth bars that we have, the default one is a smaller one, where it's normally used for very low to non-data transmission, and it allows for power saving. So this bandwidth bar inactivity timer triggers the switching to the default bandwidth bar. And the values for the inactivity timer, they vary, but normally would be something between 2 and 115 milliseconds. Then the question is, okay, who configures this? Again, it's the scheduler. It's up to the implementation, and it's left to the service providers to select a value that is not too low, but it's also not too big. So it's their job to configure it as they better see fit, and the values that allow them to get the best performance out of the network. Okay, and then with this switching comes something that is actually